So let's get started with our very first talk, I would say. For that, we have Arthur Gervais. I see you there. You can come up stage. Big round of applause, please, for our first speaker, investigating AI and security. So the stage is yours. Thanks for joining us. And
good morning. Thank you so much for the introduction. All these blockchain use cases, they essentially rely on one property that blockchain should provide, which is security. Right? So we have to make sure that smart contracts and the applications that we write on top of blockchains are secure. In this talk, I'll try to explore to some extent to how we can use AI, where it can help, where it may not actually help too much at this point in time. And yeah, let's look at the promises and limitations. So my goal for this talk is really that you can the clicker doesn't seem to operate. Yeah, I think it's on. No worries. So you can see here this dark forest, right? I chose this image not only because the space is quite obscure, right? There are a lot of like adversarial actors. They're trying to extract value from users that are performing swaps, trades. But also you can see there are many paths, right? So you kind of, as a user or even as an adversary, if you want to find vulnerabilities, you actually don't know which path to take. So ideally, we would like to come up with solutions that find the right path among this dark forest so that we can identify vulnerabilities, preferably before we use smart contracts in production. Okay, so this is kind of like the image or the idea of the image that I would like to have. So my goal of this talk is really to show you we can, thank you so much for that, we can find a path, right? We can find like an illuminated path in this forest towards secure smart contracts, specifically towards, okay, if there's a vulnerability, we find that vulnerability, we find that path, right? So that we are not stuck in this dark forest, so to speak. The clicker still does not seem to work. Okay, thank you. So here in this image, right, you can see if I would like to find a vulnerability in a smart contract, right? So let's say you give me your code, and I'm now supposed to look through it. I start reading it. I see some variable names. I see some functions that you have. I see some logic that you have. In the sense, I should try to identify what is going wrong, what can potentially go wrong with your smart contracts, right? Because if I don't manage to find the vulnerabilities, then this is what we're going to see. We're going to see roughly $1 billion lost per year in smart contract attacks, roughly 500 million per year lost in or gained, depending on which side you're on, arbitrage, liquidations, sandwich attacks, etc. Right? So these numbers are not small, right? So we have to, as a whole community, we really should try to minimize this damage in order to increase the trust that blockchains are supposed to provide. Okay? So if you look at the list of existing security incidents, so this is actually a really nice website provided by BlockSec, for example. You can see here, I mean, many of these incidents are, I mean, this is just the summer, right? Like hackers have been busy really all over the summer. So this is the last incidents, I think, was in September. And we are supposed to, there were attacks like this whole list actually stopped in July, right? So I'd like to explain what is really an attack, right? So let me walk you through what an attack is, because so far I've been rather abstract about this concept of an attack or vulnerability. I'll give you a very simple example. Bear with me, the more technical people, it may be overly simplified, but I think it extracts the essence of what you need to know about an attack. So there's somebody, like an attacker, it can be me, it can be you, it can be some other person. This attacker has a certain address. So this attacker is then sending a transaction or starting a transaction, let's say. Right? So in this transaction, what it's doing, it's calling an action of a contract. So in this case, it's a contract A, right? So some contract A that has a function, let's call it setOwner. So the attacker calls the setOwner function of contract A and sets the owner to be the attacker. And then the second action, next slide please. The second action of the attacker would be, for example, a mint operation. Right? So you call the mint function, and again, you pass the parameter, send the minted coins to my address, right, which is the attacker address, and that's it. That's a possible attack, right? There have been such attacks out there. I can show you on chain, on several chains, whether it's Ethereum, Binance, other chains. There are such cases, right? So now the path here for the adversary is rather clear, right? You can basically you see, okay, this is the path to extract value. It's very clear on how this attack can be executed. However, if I'm now supposed to be the good guy, I'm trying to find an attack in your smart contract, I have a variety of possible choices that I need to select from, right? So, for example, here, if, oh, sorry, could you go back, please? One more? Thanks. So here, for example, we have action 1, right? So the attacker has to choose among a set of possible options, what is the first action I'm going to choose? Which is the next most likely action that will yield, that will result in an attack, right? So this is essentially what the attacker or me, if I want to secure a smart contract, I have to choose. I have to guess an action. Once I have selected action 1, I need to select action 2, action 3, and so on, right? So you see, it's quite like a dark forest. A lot of possible paths I can choose to follow, and I don't know which one will yield to success. Anybody already guessing why I'm talking about paths, combinations with AI, right? So let's talk about AI a little bit later, still a bit of introduction. So here, another example of how can we find an attack. The previous example was only with one contract, contract A. Here now we have another possible exploration space with 2 contracts, contract A and contract B. But it's the same, right? It just gets more complicated with more contracts. Okay, next. Yeah, so it's still a dark forest, right? So let's move forward. Next slide. So the first question, if we tackle this problem from a first principles perspective, we can ask ourselves, so how many contracts do we need to actually carry out an attack? Right? How many smart contracts typical attacks are exploiting? I mean, how many contracts are involved in an attack? Well, if we look at the data, and this is just a very preliminary study here, next please, it's roughly 3 to 4 contracts. Roughly 3 to 4 contracts would cover probably 80 to 90% of all attacks. And when I speak about attack, I really mean attacks that extract value, and we have over 400 cases well documented online, right? There are these resources, as I mentioned earlier, like BlockSec. There's DeFi Hack Labs, has a fantastic data set of proof of concepts. So we can measure this rather easily. Next slide. The next question is, how many actions does an attack need? Right? So remember, a contract has a list of functions. We need to choose a certain function, so that I call an action. And here, contract A, for example, we choose the set owner action, right, or function of this particular contract. So in summary, it's roughly 3 to 5 actions, like core actions, that would cover most attacks. Right? So they're not that complicated. Right? So the search space doesn't seem too large. Right? Okay, next slide. Now the next question is, how many parameters does an attack need? So in my really simple example here, you'd see there's only one parameter, it's an address. So we send something to an address me. So maybe most attacks only need like 2 to 3 key parameters. There's a lot of noise typically in blockchain transactions. They look far more complicated than they actually are. So I always encourage you to really distill the essence of an attack to understand the core. So can we use exhaustive search, right? Only 3 to 4 contracts, 3 to 5 actions, 2 to 3 parameters. Well, it still seems to be too much, right? So exhaustive search sounds great because you're really like crawling the entire space. But if you have a parameter like an integer, right, which can vary in terms of range significantly, or if you have a parameter that's a byte field that requires a cryptographic signature, it's really tough to exhaustively search through that space. Okay, what kind of AI techniques can we use? Well, let's just dump the source code of these smart contracts into ChatGPT or Claude or your favorite open source LLM. Would that work? We tried in a very naive way, and it doesn't seem to give very encouraging results yet. I think there's a whole body of work being worked on to actually improve these kinds of techniques. And if I tell you something doesn't work, you should really challenge me, right? What is he talking? Like, prove me wrong, please, right? I'm sure these LLMs will be able to yield less false positives in the future, but for now, their false positive rate is rather high, unfortunately. Okay, so can we ask a large language model for the sequence of actions, right? So an attack essentially is a sequence of actions with parameters. So can we just dump the contracts into a large language model and ask it, so which sequence of actions and parameters should I try? It seems to work in some cases, but from our experience, the more precise you are in your question, the better results you get from LLMs. So far, this seems to help, right? You could, for example, ask here the LLM, you can write a prompt. I have this contract A with the function min, set owner, burn, swap. Which function should I call in order to extract value from that contract or from another contract? Right? So that's a possibility, but it doesn't seem to yet work too well either, at least from our preliminary experiments. Again, prove me wrong, right? Try things out yourself with different models, with different prompts, etc. Third example. Next slide, yeah, thank you. So the parameter guidance, right? So this is a very specific example. So let's say we have the following smart contract here. I won't go into much detail, but essentially it's a smart contract with a byte parameter here, right? The score number. In order to create valid input, right? If you want to explore this search space, you need to create very specific values, right? So what an LLM can probably help quite well with is you pass it this code and you ask the LLM, could you please generate values that would allow me to execute all branches in this code? So it's a fancy way of generating test cases, right? So this seems to be quite promising, and this may help, for example, these exhaustive search tools, or also called fuzzers, to trim the space of variables quite well. Okay, so something seems to be promising here. So I'm trying to give you a few avenues, right, where things may work, may not work, and it's really up to you to challenge whether I'm also right, because we only try so much, and things may fail, things may work out, etc. Right. So we have implemented some of these techniques in some variation in a search tool. So these search tools are called fuzzers. And currently we find roughly 2 more than the existing state of the art in terms of vulnerabilities. Right? That's 2x is good, but it's still not enough, right? We need to really find all vulnerabilities ideally. Also, this 2x means that currently on the subset of the existing data sets, it means we have a 25% chance of finding vulnerabilities, right? If there's a vulnerability. So it's a good number, but there's still much to be done, still a lot of improvements to be made. Okay, so far, one slide back, please. So far, I've primarily spoken about vulnerability search, right? This is only one component of a smart contract security lifecycle. There are things pre-deployment, post-deployment, and there are things you can do post-incident as well, right? Once you have been hacked, often hackers leave money on the table and you can take the remaining funds, for example. I would like to dedicate the rest of the talk to intrusion detection, which is not vulnerability discovery, but rather once there's an incoming attack vector, like an incoming attack transaction, can we detect that one? And let me give you an example of how you could build a GPT model, like a base model, next slide please, on how to do this. So GPT training pipeline is typically 4 steps, right? Pre-training, supervised fine-tuning, reward modeling, reinforcement learning. Then you get something like ChatGPT. In this talk, I will really just focus on the first step, this pre-training phase here, where you get, at the end, you get a base model. A base model is something that is a document completion model, right? So you put in hello, and it may return hello world, and it's a completion model. So the challenges, next slide please. the challenges of using conventional ML-based intrusion detection systems is that we typically do need some binary classifier, right? Some function that says, okay, this is either an attack or a benign transaction. And we have roughly 400 attacks out there, right? Against smart contracts, high value attacks, in fact, each above $100,000 in value. But 400 is nothing for traditional machine learning methods. So the labeled attack data is still really, really narrow, and attack patterns do evolve. Attackers do get smarter over time. So that's a challenge. Now, the dataset that we use is actually an unlabeled dataset. So we take roughly 70 million transactions from actually a few years of victim smart contracts. And on these victim smart contracts, we have a ground truth dataset of attacks that we know happened against these attacks. And we use this ground truth dataset only for validation, not for training. So we can train just on pure data. So what do we train? Next slide, please. So we train a base model, right? So a BlockGPT model. So specifically, we try to estimate how likely is this given transaction that is incoming, how likely is this an attack, right? Because it would look rather different to the other 70 million transactions. So what we can do is we can put in here in the first step, we put all 70 million transactions, and then we put in a new one, and we ask this model so there's a training step, right? Step number 1, training. Sorry, could you make the training step? We train the model, and the second step is the inference, where we ask the model, given this new transaction, what is the likelihood that this is an abnormal transaction? Please rank it by abnormality. Sorry, still back. So here you can see we can then define an alarm threshold, which would define how many false positives we are also happy to accept, right? So this method does have false positives. It depends on how sensitive you want to be. Next slide, please. So if I would go a bit more technical, I would just give you a very high-level overview. So we take a transaction. We tokenize the trace of a transaction. A trace is the execution lock of a transaction. We embed the trace. And then we can derive, with the help of the model, of the BlockGPT base model, we can derive a likelihood of how abnormal that transaction is, right? So for this, so the advantages of this kind of approach is there are no engineered rules. This is fully data-driven, right? I have no heuristic whatsoever. Like I could define heuristics, for example. If the transfer has at least $100,000 worth of value, right? And the sender is taking a flash loan, whatever, right? I could define these heuristics. They're not necessary here. This is fully data-driven. So it means it actually detects attacks for that are not covered by any known rules. And I think more interestingly, it even detects non-profitable sanity check transactions. So we have sometimes we have seen attackers creating transactions that almost extract no value, like maybe $100 of a DeFi protocol, like of a smart contract, and these are detected by BlockGPT. Next slide, please. So BlockGPT is really just a very basic prototype. I would say it's even a research prototype. It's not ready for production, but it's the first method that uses unsupervised learning for smart contract detection. Right? So I really encourage all of you, just like as I asked you to challenge me whether something works or doesn't work, also challenge me here to build a better base model that has better detection rates, less false positives, and maybe even a higher throughput. I mean, we already measured a throughput of 2,000 transactions per second, which was easy on one GPU, right? So I think throughput is not a problem with these kinds of systems, but accuracy and false positives are still definitely work to be done. Cool. Yeah, the paper's online also here, and yeah, with that, thank you. I'm happy to take any questions, and I would like to provide a shameless plug. If you want to go deeper into DeFi and smart contract attacks, please check out this DeFi MOOC, massive open online course with other leading universities. Thank you.
Can you? You hear me. Yes. Thanks for your talk. Very interesting. So now we have time for questions from the audience. If there is one, stretch your arm or something. Okay, it's too early, right? Coffee missing. There's one.
Hello, thanks for your sharing. I have a question about the attacks, and you have talked about your GPT tools can detect attacks. And my question is, how many kinds of attacks could you detect? Because I have seen you have explained one kind of attacks, and whether there are many other kind of attacks, and can you also detect them? Thank you.
Yeah, thank you. Great question. Can we go back to the, I think, like 3 slides maybe? Oh, sorry, 2 ahead. One more. I think it's number 25. Yep, perfect. So here, what I try to quantify is like out of 124 attacks, right? So this is the ground truth data set of how many attacks we consider in this work. In BlockGPT ranks 20 as the most abnormal transactions. So you can, the way we evaluate this, and there may be other ways that are better, but the way we chose is we have a smart contract. That's the protocol that gets attacked, right? Then there is an incoming attack transaction that tries to extract value from that smart contract. We ask BlockGPT from all the transactions that interacted with that victim smart contract and this new incoming vector, please rank these transactions in terms of abnormality, right? So BlockGPT in this specific case ranked 20 of the attack vectors against these overall 124 protocols as the most abnormal. So if you select an alarm threshold of 1 transaction, then you would find that attack in 20 cases out of 124. That's kind of your detection rate, right? If your detection rate is a little bit looser, if your alarm threshold is a bit more flexible, then you do have 40 more attacks, because a further 20 are ranked as the second most abnormal, and then 7 are ranked as the third most abnormal. Now you asked me about the type of attacks. We simplify slightly. We kind of consider we don't care about the where, or like we don't care about how an attack is executed, right? All we care about is there financial value being extracted? Is there an attacker that gains financial value and a victim that loses financial value, right? If that's the case, then that's an attack. So we abstract away a bit from the technical underpinnings of why that kind of attack would occur, whether it's an integer issue or some access control issue or something else, doesn't really matter, right? So BlockGPT should cover all of these. Yeah. Thank you.
Hello. Sorry. Still getting our tech together. There was one other question I've seen.
Thank you. So I was wondering, how did you select it, and what method you used to select the database, and how you deal with overfitting?
Right. So the data set was 124 attacks. At the time we did this research, this was, to my understanding, most of the DeFi attacks or smart contract attacks on Ethereum. I mentioned the number 400 before. The number 400 takes into account other chains like Binance and so on, right? So on Ethereum, I think at the moment maybe there are about 150, maybe 200 attacks. So it's almost all the attacks on Ethereum. So from that angle, I think the dataset is rather comprehensive. However, regarding overfitting that you're alluding to, I think so we have not incorporated. So in our dataset, we have not incorporated benign. DeFi protocols that are not being attacked. We only have DeFi protocols that are being attacked. So I think follow-up work should certainly include additional transactions from protocols that are not being attacked. Very good point.
Awesome. Thanks for that answer. I think we would have time for one very short question, otherwise we have to wrap it. There's none? Oh. Quick one? Like, is it a short one or somewhat short? Okay.
Hi, thank you for the presentation. Why ranking, not scoring?
What is scoring?
Like giving the score of abnormality to a transaction rather than ranking it relatively to the others. Like, seems like almost the same thing.
Of course. You could also do that, indeed. So we chose a relative threshold, so like the abnormality relative to other transactions. I think you could also choose an absolute threshold, right? That would be scoring, as I think you suggest. It's also an option. I think that was an arbitrary choice, but maybe it's not the best choice. Very, very good point. Yep. Future work.
Awesome. Thanks for listening. This was our very first talk. There are a lot more to come. So big round of applause for our very first speaker.
Thank you, everyone.